Hello everyone and welcome back. We're picking up where we left off at section 2.2. This next section is a little bit on the long side, so we're going to break it up into a couple videos. The goal of which will be to emphasize some different aspects of the types of examples that appear in this section. So today we're just going to look at some of the simplest examples, and then next time we'll look at some slightly more complicated, also some slightly more common, well, maybe not more common, but more diverse examples, more general examples to say the least. And then finally, we'll conclude this little mini series on examples with a distraction video where we will pursue some examples of limits and colimits in topology and in geometry. So let's start sort of demystifying some of these concepts by just looking at some concrete settings. And so we'll start with a definition. This will be our most common or most basic example, probably the most example most of you are familiar with, which is as follows. We take a family of objects, xi, in some C. We don't worry about what a family means, but we insist that I be in some bigger indexing set, capital I. And if this I, as is said, if we regard I as a discrete category, well, you remember that a discrete category is a category with no non-identity morphisms, then we can define the coproduct to be the limit that you get, or the inductive limit, the forward limit, sorry, I had to have a think there for a second, of the functor alpha, which just takes this I onto these xi's respectively. And then similarly, we define the product to be the projective limit. And already we get a couple of nice properties from this. Like, you know, if I assume that you guys didn't know anything about products or coproducts, already this would capture something useful for us. For example, probably in your algebra classes, you learn that hom into or out of a coproduct, usually we denote this by the lowercase, sorry, not the lowercase, the upside down pi for the coproduct. That this sort of doesn't quite commute because hom is arrow reversing. Whoa, what am I writing? I want the product of the homs. And in the first argument, we have similarly, or sorry, in the second argument, we have similarly that the product of the xi's is the product of the homs. And we recall that we talked about this idea that about thinking diagrammatically about limits, that when you have a representable limit, that you can sort of think of these things as, if I have some hom y for some limit y, then this is the same thing as alpha I y. This business of the evaluation maps. You take the identity map, and we said that this obtained some compatibility relations between the objects that we're taking the limit of, which were defined by the morphisms between the objects. Well, in this example, there are no morphisms in I whatsoever, except for the identity morphisms. And so the diagram that we produce looks like a family of xi with a big product above, mapping down. And similarly for the coproduct, except in the reverse direction. And if this looks weird, well, just think about what happens in the two-object case when I is like, you know, just 1 and 2 respectively. Then what we obtain is the product of two x's mapping down to their individual factors. Oftentimes we would name these guys by lowercase pi's. I don't know, I guess these guys are usually maybe denoted by other i's, but I've already used I, so I'm going to use j. I'm going to call this j subscript I because that sounds silly. And probably you see in your algebra class, you learned that if you have any object y, then specifying maps from y to x1 and x2 is the same as specifying a map into the product. And this is exactly the diagrammatic thing that Kashiwara and Shapira show us in this general case. They allow, of course, more complicated diagrams, but this is the specialization of that general nonsense to this situation. And in the reverse case, exactly the same thing happens with the coproduct. If I form x1, usually written as box for what is often thought of as the disjoint union, in different categories it appears as different ways, then the arrows go the opposite way, but the story is the same. My arrows go this way now, and we obtain a diagram like this. And these are the universal properties of the product and coproduct. Hopefully this is a thing that everyone is sort of familiar with. I just wanted to take the moment to sort of specify, show how we obtain the familiar situation from the abstract nonsense. Now the next thing we're going to do is sort of a kind of also example inspired from algebra. And for this, we need a special category. So I realized after writing my notes for this video that I wanted to call this category 2. But 2 is a category that already sort of exists. It's a category with 2 objects and an arrow between them. But I want a category that has 2 objects and 2 arrows between them. So I don't know what to call this category. I'm going to call it 2, 2, 2, 2, because it's 2 objects and 2 morphisms between them. Or maybe I won't call it anything, and maybe I'll just call it this picture. We'll see how much that matters. I'm just going to make it up as I go. All right, so our next example uses this category rather extensively. And all that matters really is we're going to need some functors out of this category. So what we do is we define the cokernel, also called the co-equalizer. Helps include the missing E. The co-equalizer of a pair of morphisms which we might call FG, respectively, to be the limit of alpha, where alpha goes from this weird category with 2 objects and 2 morphisms into whatever other category. This will be part 1 of our definition. And then we define the kernel, also called the equalizer, of a pair of morphisms to be the same thing, except we take the projective limit. And now we speak of sequences. If I have a sequence x0, x1 with a pair of maps, and then mapping to some z, or respectively, z, whoops, that's not where the double arrow goes, z to x0, and now double arrow to x1, then we call this is exact. If z is isomorphic to either the cokernel or the kernel, or to I guess I want to say, yeah, to the cokernel of the kernel of the pair of arrows. And these definitions really just sort of warrant some demystification. Like, I spent a fair bit of time when I first saw this just sort of confused about what this has to do with a usual notion of kernel and exactness. And this is sort of what motivated splitting the video into 2. I thought about this for a little while, and then after figuring it out, I felt kind of silly. But I said, well, if I have to figure it out, probably I should elaborate on it. And then, of course, also, we should say, what on earth does this have to do with exactness? I'll try to say a couple words about homological algebra and sort of what that means, but if you haven't seen this idea, well, don't stress about it. We're going to talk about homological algebra and some level of generality later. So, in order to get started, let's make sense of this starting with kernels, because kernels are of the 3 of them. You need to know about kernels to talk about exactness anyway, and kernels are less mysterious than cokernels. So let's just start out with the most basic concept of a kernel. When you're in linear algebra or group theory for the first time, you deal with objects, maybe vector spaces, maybe groups. I'll think about groups for now, but it doesn't matter. And I have a morphism of groups, and then I have a group phi, G to H. Then with the kernel of phi was all the stuff such that phi of G is sent to the identity in H. And we need to find a way to sort of capture this in a categorical way in order to sort of make this analogy and justify this terminology. In order to make this analogy, we would, like on the nose, like to make a precise version of this analogy, we would need to have categories that have enough structure in them to talk about things like zero in an object. So you'd have to have sub-objects. And we're not going to worry about that. Like, in order to make sense of this definition, we're not going to stress about what properties it takes to make this make sense. We're just going to assume our category has as much stuff as it takes to make the definition work. And then once we've got that, we'll go from there. So if we had a single morphism and our object, and the object our morphism takes values in has a zero object, then what we're going to do is sort of pretend that the other object, the other map, sorry, in our definition of kernel was just the zero map. Like the map just hitting that zero subobject and only that zero subobject. Then the kernel would be the subobject for which the given morphism, like this guy phi here, because let me write this in. There's also sort of hidden guy 0 here. Okay, yeah, so after making this pretend morphism, the kernel is the subobject for which the given morphism and the zero morphism agree, or in other words, are made equal. So the kernel is the stuff in G for which phi G to H and 0 G to H are equal. So what's going on here is basically we're trying to fit in an object, ker G, which goes into G, and then we have this pair of parallel morphisms that looks like this. And that sort of looks like the previous diagram. So we're on the path. So now what we want to do is be able to handle this in the case where one of the morphisms is not the zero morphism. And when you're in a sufficiently enriched category, whatever I mean by that, then you can add and subtract morphisms. There's a term for this. It's called pre-additive, but we're not going to need this for a while, so don't worry about it. But in that situation, we could define the kernel of a pair of morphisms to be the kernel of the difference. So maybe I'll just say, in suitable contexts, it makes sense to say that the kernel of fg as a pair will just be the kernel of f minus g. And this has the same sort of effect, right? This will be the situation where f and g, where the kernel of f minus g is 0. Well, when does that happen? That happens when f and g agree. So this is sort of capturing our idea that the equalizer should be the object that we use to fit two things together. And so we take this to be our definition, or we take this diagram to be our definition, even in the case when we can't actually take the difference. And that's the source of our this categorical definition. Okay. Now let's think about cokernels. So just sort of, we want to dualize this discussion. And the way to start thinking about this is to think that if the kernel is sort of the largest object or the universal object on which a pair of morphisms agree, then the cokernel should be the sort of opposite of this. So what's that? Well, should be the smallest object that we can obtain by forcing two things which don't agree to agree. So instead of looking at where they do agree, we look at where they don't, and then we deal with that. So that sounds sort of vague and philosophical. So in order to get started, let's again just sort of look at some familiar cases that we understand well. And as always, the best example is linear algebra. So let's just think we have a linear map v to w. And we're trying to figure out, again, just to think about the one map case, the cokernel where the second map is the zero map. And if we figure that out, then maybe we'll be on the path to figuring out what we want to do in general. So what we want to do is find an object now which has to lie to the right. So we're looking to extend this, and we have our hidden zero guy, to another guy, which we might call x, which should make this diagram commute. So what this means is that, how do I want to say this? In other words, whether I look at the map from v to w as either t or 0, I need to get the same thing. So whatever t hits has to be killed, because I need to force these things to agree when I then apply the map from w to x. And so what I'm doing then is taking x to be w mod the image of t. Yeah, that's right. And this is, of course, a perfectly natural thing to do in vector spaces. Quotient vector spaces are easy to form. You just, start with a basis which includes the image of t, and then complete it to a basis of w, and then just whatever my vector is in w, I write it in that basis with coordinates, and I set all the coordinates coming from the t guys into 0. So for a pair of maps then, we want to sort of continue this process, and we want to do exactly the same thing. You could play the game where if I have two general guys, maybe I have v to w, and I have two guys t and u, I could define the cokernel of t and u to be the cokernel of the difference again, and everything would work exactly the same. Maybe I want u minus t. It doesn't really matter. Maybe I want the sign to work out nice in practice, but I don't care for this discussion. Because the difference of a sign is just an isomorphism. So just pay attention, but it doesn't matter. What this would do then is basically force u and t to agree. We're sort of taking the stuff in u and t and saying whenever they disagree, well, we'll force them to be the same by just making it 0. And in categories more complicated than vector spaces, cokernels are a lot more complicated to describe than kernels in this nice sort of explicit way. Vector spaces are nice because you can sort of describe everything cleanly. But in general, it's hard to say much. The one thing that is worth pointing out is that in this example, with vector spaces, I actually don't use the full vector space structure. Like I'm just using the ability to add and subtract things. So the same fact should be true more or less exactly the same in abelian groups. Sort of further similarly in sets, you can say some things now that I'm thinking about it, because even in sets, you can't add and subtract. You can still quotient really easily. In particular, if I wanted to take a co-equalizer of a map of sets, well, that would be just applying some equivalence relation that forces f and g to agree all the time. And then whatever set you get when you impose that equivalence relation would be the co-equalizer. In general, I don't know too much more that I can say. I've seen particular examples where I can do computations where you can figure it out, but these are sort of more mysterious objects. It's sort of our principle that while you can prove things in general, the dual object is sort of very different from the original object. One thing that is worth noting, a positive statement that you can make, is that for kernels, you have this fact that says a map, maybe I'll call it, I was going to write t, but maybe I should call it something else. If I have some phi, then it's a fact that hopefully everybody knows that phi is injective if and only if the kernel of phi is 0. And similarly, at least when you're dealing with concrete things, maybe you have to work a little bit to make sense of this with monos and epics in general, but when you're working in the concrete setting, you have an analogous fact, which is that phi is surjective if and only if the cokernel of phi is 0. So maybe another way of thinking about cokernels then is that the cokernel is the obstruction to surjectivity. It's sort of like the smallest thing that you can make sense of, which is sort of the complement of the image. And normally complements of things are not nice things. Like in a vector space, the complement of a subspace is not a nice subspace. But if I take the quotient, then what survives, the equivalence classes are sort of all the things not in the span, which is sort of like a complement, but adapted to the setting of vector spaces. Okay, Um, if you want to see more examples of this kind of stuff, I think I want to sort of call it quits here for cokernels, and I want to talk about exactness. So maybe you should take a look at a book that takes a more scenic view, like maybe Emily Reel's Categories and Context talks about this, or McLean's Categories for the Working Mathematician. Okay, let's move on to exactness. And we're going to start with a brief reminder of what exactness means in the classical setting, in case you haven't seen it before. And in homological algebra, exactness is the following. Suppose you have three modules over a ring. Let's call them A, B, and C. And I have maps between them A, B, and C, like so. We call this trio exact. I should name these maps. Let's call this one phi, and let's call this one psi. So this trio is exact when the image of phi is exactly the kernel of psi. And oftentimes we extend these sorts of things in some special cases. Like, for example, if the map from A to B is injective, then we know its kernel is 0. So I could get the same thing by putting a 0. Let me scroll. That's too far. If phi is injective, then the kernel of phi is 0. And then we could ask then for something where the image is also 0, and namely 0 itself has that property. I just take the 0 map. So I could include like so. And similarly, psi surjective implies the cokernel is 0, or what we just said. So we could extend also and get what's called a short exact sequence here with zeros on the end. And you don't have to stop here. You can make pretty much any sequence of maps and call them exact whenever the image of any of the maps is exactly the kernel of the next map. And if you wanted to speak of an exact sequence, then you would require the first map to be injective and the last map to be surjective. Now, something that you can do with this that's very helpful in the case of modules is basically the fundamental theorem of linear algebra, this business of the rank nullity theorem, which basically says if I have any map, maybe it could be vector spaces, could be modules, doesn't matter, V to W, then I can always make this into an exact sequence, where I can start by including the kernel, if I call this guy T. I can include the kernel of here, and then I can include the cokernel afterwards. And now this has to be exact, because the kernel of T maps into V. That's exactly what's killed by V, so the image is exactly the kernel of this map. Then I map V to W, and then of course what am I killing when I take the cokernel? Exactly the image. So I extend this to an exact sequence, like so. And this is our inspiration for this definition in Kashiwara and Shapiro. Oftentimes in practice, one can truncate this sort of thing. You may be only interested in certain aspects. There's nothing wrong with just ignoring things. So in Kashiwara and Shapiro's definition, what's going on is that they're looking at the sequence V to W to the cokernel. And they're not really interested in what else there is. And so they call this thing exact when the object that you want to put on the right of the map from V to W is exactly the cokernel. So this definition is just inspired by the sort of classical linear algebra case, except Kashiwara and Shapiro do the slightly more general thing, as you always do when you're sort of interested in category theory, where they allow this thing to not be the cokernel exactly, merely isomorphic to the cokernel. But otherwise, it's exactly the same, and also the same for kernels. They put, of course, the kernel then goes on the left, and that's what happened with the Z object in that case. Okay, so I think we're going to wrap things up here. It's been almost 25 minutes. I've been talking about this long enough. Just to sort of say where we're going, the next family of examples that I want to talk about are examples that are modeled on more complicated categories. So every example we gave today was modeled on this category with two objects and two morphisms, two parallel morphisms like so. And now the next step is to talk about limits of things where the model category is sort of bigger than that. And the best example are three object categories. So maybe I'll just write this down. Next time, the models will look like this, or they're duals. Or maybe just something like things that are maybe more complicated but built out of these as building blocks. Like the first example I gave about products. Well, it's not really necessarily a 2-point category because maybe you had some big family. But if you understood sort of what happens for the two-object case, then you sort of understood how to put these together to generalize it. And so maybe what I'll say is the fundamental example of products and coproducts is indexed by a 2-point category. And so the next natural step is to look at 3-point categories where the morphism can do more complicated things. In particular, they should both either point out or point in. And then in the video following that, I'll talk a little bit about what are called direct and inverse limits specifically, which are special cases where the category is the natural numbers. With morphisms either going by increasing or decreasing. So we're just regarding n as a partially ordered set. And we'll look at some examples where this kind of limit appears sort of in the wild. All right. As always, thanks for watching, and I'll see you guys next time.